Carlos Plain, a teacher from Durham School, shares that throughout his lifetime, he has focused on developing a precise and clear hypothesis of the universe. He currently sees this hypothesis being scrutinized, something he welcomes, recognizing that science advances through such challenges. The James Webb Space Telescope is revolutionizing and testing some long-established ideas in cosmology, revealing a completely new perspective on the universe. As we enter the new year, the telescope's ultra-deep field image has shown significant errors in our past understanding of the universe. Initially designed to reveal the universe's earliest stars, this telescope is evolving into a challenger to past ideas and may bring about an entirely new approach to cosmology. However, not all scientists fear these revelations. Many experts in the field embrace these changes, as it has become increasingly clear that something was amiss with the older theories. The inconsistencies in calculating the universe's expansion rate have cast doubt on previous assumptions, yet for a long time, scientists clung to old beliefs. The cosmic microwave background, CMB, considered the oldest light in the universe, originated about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to bond and form stable hydrogen atoms. This period, known as reionization, allowed the universe to become transparent to light. In 1964, American physicists Arno Penzias and Robert Wilson made a groundbreaking discovery while working with new radio antenna technology. They detected the CMB. This finding was long considered one of the strongest pieces of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and cementing their place in the history of astronomy. The CMB offered scientists a unique glimpse into the early universe, revealing small temperature fluctuations that provided insights into the conditions following the Big Bang. The CMB was also used to measure the universe's expansion rate and verify other cosmological assumptions. As early as the 1920s, astronomer Edwin Hubble established that distant galaxies were moving away from us, with their speed linked to their distance. This observation led to what is now called Hubble's law, or the Hubble constant. While Hubble lacked the advanced observational tools available today, his discovery, alongside the later detection of the CMB, led to recalculations of the universe's expansion rate. These calculations revealed a slower expansion rate than Hubble's original estimate. Later astronomers used Type Ia supernovae, known as standard candles due to their consistent brightness, as reliable measurement points to gauge vast distances. These recalculations, based on the CMB, suggested an expansion rate of approximately 67 km per second per megaparsec, while measurements from supernovae indicated a higher rate of about 74 km per second per megaparsec. The disparity in these calculations has been a contentious issue for scientists for decades, with many researchers recognizing that something was fundamentally wrong with how the CMB and the universe's expansion rate were being interpreted. This inconsistency, known as the Hubble tension or SAA anomaly, suggests flaws in our basic understanding of the universe. These discrepancies have significant implications, challenging our most fundamental beliefs about the universe's workings. The issue has been known since the 1990s when scientists began to suspect errors in the methods used to measure the CMB or in the assumptions about the universe's expansion. Over time, the gap between observed and predicted expansion rates became increasingly evident. The Hubble tension implies that our theories may require a drastic overhaul, indicating that key elements of our cosmological model could be deeply flawed. Now, with the advent of the James Webb Space Telescope, researchers are gaining unprecedented new data that could help resolve the issues with our understanding of the universe's expansion rate. These new findings are so significant that they could shake the very foundation of our past cosmological theories. The telescope is uncovering galaxies and systems so old and evolved that they suggest the universe's development may have begun well before the Big Bang. This challenges old cosmological views, forcing scientists to rethink the nature of the Big Bang and the formation of the universe itself. Instead of merely debating errors or inconsistencies in data, scientists are now addressing what many describe as a crisis in current cosmological models. It's no longer just about mistakes, it's about rethinking our very conception of the universe. The new data from the James Webb Space Telescope reveals a universe far more astonishing than previously imagined. The Hubble tension, once a source of confusion for those clinging to traditional theories, is now a focal point for scientists who must confront the possibility that our understanding of the universe might need to be completely redefined. As scientists continue to analyze these groundbreaking discoveries, they are also grappling with a larger question: do we truly understand the universe? To answer this, it's essential to grasp how science works. Cosmologists use complex mathematical models, careful data analysis, and logical reasoning to make predictions and test hypotheses. Their conclusions rely on a combination of empirical evidence, well-established principles, and theoretical calculations. However, it's important to remember that science is a dynamic field, and theories are always subject to change as new data emerges. The term hypothesis itself suggests that scientific understanding is an ongoing process of refinement, not absolute truth. One of the most critical sources of data for cosmologists is the light captured by telescopes, as well as the radiation and sound waves detected through radio telescopes. More recently, neutrino detectors and gravitational wave observatories have expanded our understanding of the universe. The James Webb Space Telescope provides an invaluable tool for studying the earliest galaxies, their structure, mass, and the number of stars they contain. It can also trace the formation and evolution of galaxies over time. However, Webb is not without its limitations. For example, it is sometimes difficult to distinguish distant galaxies from massive black holes that produce similar levels of brightness. This recognition forces us to acknowledge that, for a long time, science may have accepted certain assumptions as facts while dismissing other possible explanations. The new discoveries from the James Webb Space Telescope highlight the importance of remaining open to new ideas and theories. The data gathered by Webb presents a critical opportunity to replace outdated models with fresh perspectives, much like how science has always progressed through revolutionary discoveries. As scientists continue to unravel the universe's mysteries, they face the challenge of developing new explanations for what they are uncovering. These revelations are causing significant shifts in the foundational concepts of our understanding of space, prompting a reassessment of our knowledge of cosmic expansion and the forces at work in the universe. Our current models of physics and astronomy are still largely rooted in the 17th century laws of Isaac Newton. While his laws of motion and gravity have served as the cornerstone of our understanding of physics on Earth, they were eventually found to need revision when applied to space. This led to Albert Einstein's groundbreaking work in the early 20th century, particularly his special theory of relativity in 1905, which revolutionized how we perceive space, time, and motion. Einstein's general theory of relativity, published in 1915, completed this revolutionary thinking, proposing a mathematical model that explains the gravitational effects of massive objects on the curvature of spacetime. While Einstein's theories were crucial in transforming our understanding of the universe, he himself acknowledged their limitations. He believed his theories would never fully account for all the complexities of the universe and dreamed of a unified theory that would encompass all of physics. Yet, no scientist has succeeded in achieving this comprehensive model of the universe. It remains an open question. What might this theory look like, and could it win someone a Nobel Prize? Among the leading suspects in the current cosmological crisis are dark matter and dark energy. These concepts, which make up around 95% of the universe, remain largely theoretical, as neither has been directly observed. While these mysterious substances are integral to current models of the universe, their exact nature is still unknown. Some experts speculate that they may not exist in the ways we assume, requiring alternative explanations for the observed expansion of the universe and the dynamics of galaxies. Others suggest that dark matter and dark energy may have evolved over time, altering their properties in ways we do not yet understand. Another possible explanation involves gravity, a force we know causes attraction between masses. Yet even this force, described by Einstein's theories of relativity, remains an area of ongoing study. Scientists are exploring the possibility that gravity could have characteristics we do not fully comprehend, or that an entirely unknown force might be responsible for the gravitational interactions we observe. The discoveries made by the James Webb Space Telescope and other advanced tools demonstrate that the pursuit of knowledge is never-ending. With each new observation, researchers are forced to refine, revise, or even abandon previously held ideas. This process of scientific evolution ensures that our understanding of the universe grows more accurate over time, even if it challenges long-standing assumptions. As we grapple with the complexities of dark matter, dark energy, and the apparent inconsistencies in the universe's expansion rate, we are reminded of the humility required in scientific inquiry. The questions we face today, about the true nature of the universe, its origins, and its ultimate fate, may seem insurmountable, but they also drive innovation and curiosity. Scientists now look to new theoretical frameworks, combining advanced technologies with creative thinking to tackle these mysteries. The implications of these findings go beyond cosmology. They force us to reconsider humanity's place in the cosmos, inspiring awe and a sense of wonder at the vastness and complexity of the universe. Whether the answers lie in new physics, alternative interpretations of existing data, or discoveries yet to be made, one thing is certain. The journey of understanding the universe will continue to shape not only science but also our broader view of existence itself. As this pursuit continues, the scientific community remains at a crossroads, with new technologies, discoveries, and theories converging to challenge the boundaries of our understanding. The James Webb Space Telescope, for instance, is not merely an observational tool. It represents a paradigm shift in how we approach the study of the cosmos. Its ability to peer into the depths of time and space has sparked debates that touch upon the very foundation of physics, cosmology, and even philosophy. One of the most profound questions emerging from these debates is whether our current models of the universe can truly account for all its intricacies. If the Big Bang model, once considered the cornerstone of cosmology, requires significant revision, or is even supplanted by an entirely new framework, what does that mean for other areas of science that rely on its principles? Such shifts would ripple outward, influencing not just astronomy but also particle physics, quantum mechanics, and our understanding of the fundamental forces of nature. For example, theories that explore alternatives to the Big Bang, such as the possibility of a cyclical or multiverse model, are gaining traction. These ideas suggest that the universe may not have had a singular beginning but instead exists within a much larger, more complex reality. While these theories remain speculative, they underscore the growing realization that the universe may be far stranger and more enigmatic than we ever imagined. Meanwhile, efforts to directly detect dark matter and dark energy continue, with experiments such as the Large Hadron Collider, LHC, and neutrino observatories playing a critical role. These endeavors seek to uncover the fundamental particles or forces responsible for phenomena we cannot yet explain. Success in this area would not only resolve long-standing mysteries but could also open entirely new fields of research, leading to technologies and applications we cannot currently predict. At the same time, advances in artificial intelligence and machine learning are transforming how we analyze astronomical data. These tools are enabling scientists to sift through vast datasets generated by telescopes like Webb, identifying patterns and anomalies that might otherwise go unnoticed. Such breakthroughs in data processing are accelerating the pace of discovery, allowing researchers to formulate and test new hypotheses with unprecedented speed. Yet, even as our tools and methods grow more sophisticated, the philosophical implications of these discoveries remain deeply human. The realization that we may need to rethink the nature of the cosmos raises profound questions about our place within it. Are we mere observers in an unfathomably vast and complex system, or does our ability to question and explore give us a unique role in shaping our understanding of the universe? These questions resonate far beyond the scientific community. They inspire artists, writers, philosophers, and thinkers across disciplines, fueling a cultural dialogue about existence, meaning, and the limits of human knowledge. In this sense, the exploration of the cosmos is not just a scientific endeavor, it is a collective journey that touches every aspect of our shared humanity. As we look to the future, one thing is clear. The quest to understand the universe is a testament to the power of curiosity and imagination. It reminds us that the greatest discoveries often arise not from certainty but from the willingness to embrace the unknown. In the words of Carl Sagan, somewhere, something incredible is waiting to be known. With each new revelation, we take one step closer to uncovering the incredible truths that lie at the heart of the cosmos.